This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, SE Radio listeners. I'm Po Chen, Head of Engineering at QUIC. We're a cloud communications company. If you're considering building text messaging into your projects, you'll like using our SMS API. Tens of thousands of engineers around the world do. Plus, for SE Radio listeners, there's $50 of free credit to try QUIC. Just visit clicksen.com/SE-radio. That's clicksen.com/SE-radio. Now, enjoy the podcast.
Hello and welcome to Software Engineering Radio. Today, we are going to talk about the protocols of the internet. I've got the great pleasure of introducing Varun Singh. Varun is the Chief Products and Technology Officer at Daily.co, bringing over 2 decades of expertise in video communications. He previously co-founded and served as the CEO of callstats.io, a leading performance monitoring service for WebRTC. Varun has made significant contributions to the field, co-authoring 12 IETF and W3C specifications, earning several patents in real-time communications, and receiving special recognition from the ACM Multimedia for his PhD thesis, which improved web browser call quality. He earned his PhD in multimedia networks and the telecom from Aalto University, Helsinki in Finland. Welcome to the show, Varun. Is there anything that I missed in your introduction that you would like to add?
No, thank you for having me. It's a pleasure talking to you and to reflect on the last 30 years of the internet. So I'm really happy to be here.
Yeah, it is an interesting topic. So let's just dive right into it. I think one of the first topics that we wanted to talk about was this concept of protocol ossification. So what is protocol ossification?
So protocol ossification means the loss of flexibility in evolving a protocol. And in this case, we're talking about a suite of protocols like the TCP/IP and HTTP. Although I would say that without protocol ossification, we would not have achieved the success that we did in the intervening years. So I can talk a little bit about history and like why, like in retrospect, we call it ossification, but while it was happening, we didn't consider it as an ossification.
Sure. But before we get into that, maybe some examples of protocols that have experienced ossification and why this is such a concern?
It's a good question. So if you think about like when we talk about networking or the internet, we a lot of times talk about the OSI model, which is like the 7 layers, right? And if you think about that's existed for almost 50 years now, since the 60s, 70s, since ARPANET, and then we had TCP/IP. First we had IP, then we had TCP and such. And in the 90s, actually in the beginning of the 90s, when the web came around in 94, which is like the 30th anniversary just this year, or actually this month.
Yeah, I know.
So if you think about like when the web came around, there were so many methods of communicating on the internet. And for the web to win, we needed ossification to happen. In retrospect, ossification. So what happened was we had IPv4 specifically, IPv4 addresses that had to win. So once IP won, then the thing on top of it was TCP. TCP won the game against the other protocols. And then HTTP, which was on top of TCP, like proliferated internet, right? So today, if you think about anything, like basically everything is a web service. And everything that was not a web, like everything that we have today was also not a web service. Email, for example, like we don't use any of the SMTP or any of those protocols today. Like we just use the web. Like, we go to a website, Gmail or whatever provider you have, open a web browser, and the server sides actually still communicate in SMTP. But like for us as users, we have stopped using that. So HTTP won in some sense. So ossification is like the TCP, IP, HTTP, that trio got ossified, and everything is built on top of that. So everything that is built on that HTTP, TCP, IP foundation has to follow all the constraints of that product, all these 3 protocols. Now, so if we start to build something new, which needs to expand, like the way HTTP or TCP or IP needs to behave, then you're constrained. You can't actually do that. And one good example of that was in 2010 or before 2010, like when Web 2.0 started, that movement, Google realized that like Google was really concerned about like page load times. They were very, very crazy about it. And that was like one of the metrics which drove the idea that we had ossified. Because until 2008, like people kind of knew that we had ossified, but no one actually cared about it. It's just that when we started to focus on page load time, specifically Google, they realized that they couldn't actually push it beyond a certain point because they were constrained by HTTP in its current format and then like TCP in below that. And if we wanted to reduce the page load times, then we had to like kind of make some more changes on those protocols.
Right. Now, just to kind of explore that idea a little bit further also, right? So let's take the Google example, right? So if you're thinking as a Google engineer, you have the Google web servers and the Google infrastructure. That was already state of the art. And then around 2010, they came up with the idea, okay, let's build our own browser, right? So now you have the other end of the thing, which is basically Chrome. And theoretically, you could build in whatever protocol or whatever you wanted into Chrome. But they still were having this fundamental problem. And that's mainly because of the pieces in between. So maybe you could talk about a little bit about why that is kind of, I think, the secret reason why this ossification kind of
That's
happens.
actually a good observation. So like if you think about the networks, and like one thing that you learn in like networking 101 is like the end-to-end principle. And when you talk about the end-to-end principle, the end-to-end principle basically says that the two end hosts should decide what they want to do. They should have full flexibility, and once they agree on something, they should be able to do it. And that's what you asked. Like you said, like, you know, Google got Chrome, and Chrome gave them a big advantage of owning one side, the client side of the infrastructure, and they own the server side of the infrastructure themselves. So one big thing is the middle boxes, but more like another thing to consider is that the TCP protocol itself is actually implemented in the kernel of the end hosts. So, right, so you have the browser, which has HTTP and all these new things. It has the TCP stack, which is implemented in the kernel. And TCP is also a little bit quirky. Like it kind of depends on which side you're, the sender or the receiver. When we talk about web, most of the data is actually coming from the server side. So there's a little bit more flexibility on the server side to actually say, oh, you know, I want to send a lot of data. Like, can I send you a lot of data? And the client can say, like, yeah, send me all the data, like send me more data. So there's some complexity there that they had to go around. But more importantly, like the middle boxes. So one of the biggest constraints, like why we have only TCP and UDP, we have also other parallel protocols, SCTP and such. But because we all are connected to an ISP, the ISPs are connected to something, and then they are connected to the cloud, right? Typically, like Amazon's not directly connected to. There are all these layers of players in between you and like Netflix or you and Google, and they all have infrastructure. And initially, because of security reasons and malicious traffic, a lot of ISPs actually block a lot of the traffic, right? So like they're like the first, they call themselves the bastions of security because they're like the first thing that can either ingress or egress from inside the network. They can stop what goes outside, and whatever's coming from outside can stop inside. And they decided in their infinite wisdom that they would only allow TCP to go on out because most of the traffic was on HTTP anyway, right? So like basically you stop that. And if you remember, like in the early 2000s, there were like attacks on SMTP because a lot of like Linux devices and like other devices ran like SMTP servers locally on your device. You didn't even realize
Right,
that.
and then we had the spam problems, and you could run your own SMTP server and spoof anybody's email and all that.
Right, and people were trying to get access through like port 53, port, you know, whatever ports were open. And if there was like an exploit on like a zero-day exploit on some software that was like no one is using, but it's still running because it came with whatever you got, like, you know, whatever operating system. Basically, the ISPs blocked almost everything. So you could not start adding a new protocol on top of IP, which totally allows, like there is like an infinite space of protocols that you can add on top of. And there are like SCTP and DCCP, and like there's so many protocols there, but they can never traverse. Like they may run in your home network, but they would never go outside of your home network onto like onto the web, for example.
Right.
So the middle boxes were, of course, a bit of a problem because they were basically filtering the traffic. And Google could not talk to all the ISPs in the world, and so there was no economic action. You say, oh, capitalism would win in this case, but no, capitalism cannot. There are none of those two things. The people who want the service and people who are providing the service could not make this middle boxes to change
middle layer. Yeah.
quickly enough.
Right. So that was one of the main challenges, and also the opportunity, because it was a standard network. You could put anything on it, and everybody spoke HTTP, TCP. We had this Cambrian explosion that became the internet. I guess the next thing to talk about would be then, okay, so we have TCP, and then we have HTTP on top of it. HTTP did evolve, right? So maybe we can start from what is the evolution of HTTP. We have now, I think the recent one is HTTP 3, but we had various versions of HTTP before that. Can you kind of talk about how that happened, and what were some of the features that each one of the new versions came up with?
It's important to reflect on how evolution happened. So when we had HTTP 1.0, it was just the first attempt of getting text across the internet.
Yeah. This was 1996 or something.
94,
right?
It was public release, so that's why 30 years.
Yeah. Oh, right. 94.
Yeah, 93, yeah. 94. It was, I think, already in CERN since 1991, I think, or even before. So it had evolved as part of CERN's need for sharing data for the physics experiments that they were doing across universities and their network of servers. And then it proliferated outside of that. And when it proliferated initially, I think the simplest thing to say is it was very simple. It was text-based protocol, right? And it was
it was mainly for sharing papers between scientists. It was never meant to be a protocol for business.
Yeah, you didn't want to send a PDF across the net. So basically it was, you have text, you have some images, which is what makes up most of the scientific papers, and some level of interactivity. So you could have a talk table of content, you could jump between, so you get hyperlinking. And because you didn't need a flat file, so you could organize data, right? In some more meaningful way. So you could have an abridged version, and then you could basically delve deeper. So you had HTTP then 1.0, and I think we didn't come up with H1, H2, H3, this nomenclature, until HTTP 2, because everyone before that just called it HTTP. And then 1.1 came because 1.1 was a big change, because before that HTTP was just considered one protocol, and then HTTP became two parts. One was the syntax and the other thing was semantics. And syntax was basically the network and the format and what goes over the wire and all that stuff. And the semantics were basically headers, response codes, what's actually a method. So get, put, all that got separated. So one became the semantics and then syntax. So you could have more, you could change methods, you could add more methods, you could add more response codes, you could. So in HTTP 1.1, the biggest thing that I remember was keep alives, that came through. And then, this was around, so your timeline, when you said, 96, 97, that was the Netscape versus the browser wars. So that was the time when HTTP 1.1 came. It basically, almost all the Amazon, the Googles, they all emerged in that period of time. Yeah, super successful. And then you go 10 years forward to 2005, 2008, 2009, this kind of period where Web 2.0 came. And Web 2.0, and especially Google, we talked about they were very concerned about page load time. So they started to push. And if you think about page load time, you're just sending a piece of a page, and it could be a blank page, right? And if you just send a blank page, and if you just look at the performance of HTTP with HTTP 1.1, HTTP 2, HTTP 3, just send a blank page and see how quickly it gets across, right? And then you can add more semantics on top of it, and you say, so HTTP 1.1 and HTTP 2, the big thing was that they wanted to, and actually before HTTP 2, there were some experiments by Google called Speedy. And how Speedy worked was that it was trying to be 1.1. And they tried to change, like I said before, and you also remarked that they had Chrome, the browser. So they could change a bunch of things inside their browser that could be much faster, they had their own V8 engine and all that stuff to basically accelerate anything at the ends, but also the servers were sending bulk data. So if they could just send more data and somehow change the congestion control algorithm on their side to be more aggressive, they could. So they started to tweak a lot of things, which, if the client was still using an archaic kernel TCP, they could still try to optimize from the server side what to do. But they realized that one thing that they needed to do was increase the initial window from the initial window of a TCP. When you don't know anything about anything, you send an initial window of 2 packets. So basically, if you have to send something, you either send 1 packet, that you can start with 1 and then then increase, then send 2 packets and see.
Increase as you go
and
forward.
So the most simplest algorithm is AIMD, adaptive increase, multiplicative decrease, which means that every time you get an ACK, you basically add 1 more, but you start with initial window was 2, so you start with 2 segments. After a lot of cajoling, we increased it to 4. They wanted it to be 7, right? So basically you could send 4 packets right at the front. So they did that, but that would require updates to a lot of middle boxes and the endpoints. And if you make a new kernel today, it would still take 2-3 years before it become available. So Speedy started with the idea that there will be some changes that will happen there. But one of the things that were a big problem with HTTP 1.1 was that you could not do pipelining or multiplexing or parallel transmissions. So one of the things that we got in HTTP 1, in HTTP 2 or H2 over H1 was that you could parallelize communication. So you could get chunks of multiple things simultaneously in one connection. Yeah.
So I think earlier before that, I think they were having browsers going to opening up multiple connections to one website just so that they could load the server fast. I mean, the
yeah,
page
and there was
fast.
also basically browsers were told not to open more than 2 or 3 so there was also a limit on how many.
Yeah. They were, I think it was 6. You couldn't go more than 5 if you did 0 to 5, and after that, basically you get throttled.
Exactly.
So HTTP2 brought in this concept of parallelization and adding and kind of streams into one connection. So that was in 2015, right? I think.
So basically they presented the idea in 2010. And I think in 2012, the community was sufficiently agreed upon that we need to do this. And then 2-3 more years, and then everything got standardized.
Yeah.
But already in 2014, 2015, YouTube was probably the first one which already moved. That was the biggest experiment. And I think already in 2012, 13, they were already on Speedy for several years in H2, a variant of H2 at Google. And then when 2015, this said it was done, it was already Facebook, Google, Netflix, a bunch of them. I think in even my startup called Stats, we moved to H2 in 2017, 2016. So soon after. As a startup, it takes a little bit more time because firstly, you need validation from the market and you need a tool chain available.
Right.
So you can't actually be ahead of the curve.
So obviously, this was an innovation over HTTP, and the HTTP2 came around, and it was 2017. And if you look at the difference between HTTP, which came out, like you said, in 93, and then HTTP2 came out in 2015, which is kind of almost 20 years, right? And now immediately almost, it seems very fast that HTTP3 came out. So what was the main problem, or what was the challenge with HTTP2 that, kind of pushed them to say, hey, no, we need to kind of solve this even better, or this is not enough?
So the Speedy proposal made a lot of changes, or required a lot of changes, and not everything that Speedy wanted was done, mainly because we were still stuck on TCP. Right. So the changes they wanted to make to TCP were not really granted. And what we realized was that we can't make changes to TCP and even if we did make changes to TCP, you would still have to go to BSD, you would have to go to Linux, you would have to go to so many, Microsoft, people who own the operating systems, Android, you need a lot of people to agree on making those changes to happen. And one of the things that was in H2, which we kind of solved, was the head of line blocking in HTTP. So you talked about streams, right? But one of the things that people noticed with streams was that you couldn't actually make the servers go faster because there was still head of line blocking happening at the TCP layer below.
Could you explain a little bit about that? Because as I understand it, head of line blocking is not entirely an HTTP problem, it's actually a TCP problem, right? It's because TCP is kind of sequenced. So maybe can we go into a little bit of why this is kind of
Right. So, like, head of line blocking means that if you have packet number 3 waiting to be sent and 4 is more important, you can't do anything about that because 3 is still in the queue, right? And in the HTTP world, it was resources. So you were thinking like the main thing was that you could not download resource 2 or 3 until resource 1 was done.
in parallel until one was
right?
complete.
And so like you had these connections which you were like, oh, use connection 1 to get resource 1, resource 2. But if all your, like, let's say you had 4 connections and all of them were stuck with resource 1, 2, 3, 4, you're now blocked, right? Like you could not, like, at some point, like a user clicks something and say like, actually, I want to cancel everything. I don't really care about these 1, 2, 3.
But what was this thing about blocking, right? So why was it so easy to block a TCP connection? Was it something, I mean, because I remember back in the day when I was running, so TCP essentially was one of those things that used to guarantee, it was a guaranteed form of communication, right? So you could basically, if you send a piece of data, it's guaranteed to reach there, and it was reached there in a particular sequence, right? So it was supposed to be that, okay, if you send 3 packets, packet 1 comes, packet 2, 1, packet 2, and packet 3, they will make sure that it comes in that, and they'll present it to you in that sequence. And I think that's kind of one of the weaknesses also, right? That's one of the reasons why there is this ahead of line blocking thing,
Yeah.
right?
So think of this like if you were just sending a text file, right? Like if you're just sending a text file, basically it would start reading from the front of the file, and then just basically all the lines would appear in order. Now, if something gets lost,
Right.
and if you got, like, let's say one line is one packet for simplicity for people, right? So like you have like
Right.
1,500 lines and you'll send 1,500 packets one after the other.
Yes.
The simplest, like, forget TCP or whatever, like basically what you would say, like, there are many ways to do this. You would send all the 1,500 packets like as fast. The other side would tell you like what got lost. Then you would do a second pass and say like, oh, packet, like lines 4, 15, 16, 17, 18, 21, 22 got lost. I will send it. You'll send them right at the end. But until you got to the end, you could not present anything, right?
Exactly. So that is the head of line blocking. So even though you have like 90% of the file with you in the server, if for whatever reason one line was missing, you actually would not actually see it.
So what I explained, like what the simplest example I gave is like how FTP servers worked initially. Like FTP servers just sent like as fast as possible, reported like what was missing. You sent everything. Once they had everything, then you could see the file. So TCP or HTTP or whatever does it in a slightly different way, because if you have like 3 lines of the file, why can't you show 3 lines of the file, right? Right. But if you got line 5, like you got 3 lines, then you got line 5, like line 6, but you don't know what's in line 4. Line 4 is missing, so it'll actually stop at that point. Even though you have lines 5, 6, 7, it won't render until it gets line 4, right? And that's the initial window that I was talking about, like before. The initial window will grow. So like as the window grows, like there are more things in queue. Now, if you have more things in queue, you're kind of blocked. Like you have 17, 18, and actually as a server, you know that you're sending 19, and you actually say like maybe like line 4 is like, I'm still pending 4, but it's not needed now. Like, you know, for whatever reason, it has some context.
Yeah, maybe it's like one frame in a video, or one pixel of a frame or something.
Right. And it says like that's part of a different resource. That resource is probably under the, like you've already scrolled down further that you don't care about something there, right? So the HTTP 2 solved the resource head of line blocking in some sense, right? So resources could come out of order and be,
But even then, within a resource, if you had header line blocking, that was a problem. And increasingly in the modern web now, we've got really large resources, right? You have one file, which is a video. It could be a podcast, for example, which is several megabytes.
Yeah, and you like streaming is its own other problem, and we can come to that. There are other transports to that can help. But like, yeah, you're right. Like there are resources that are big, or there are too many resources, right? Like if you think about Twitter and like this feed that you're getting, each tweet could be its own resource, right? And like you may have scrolled past a certain resource, so you don't really need that resource anymore, but it's still in flight. So yeah, so H2 solved that. And in H3, what they made the decision. So firstly, we made the decision that we don't want to use TCP. It's too slow. Like innovation in TCP is too slow to like move forward. And so this work had already begun in 2000. I mean, even before 20, like we started working on H3, we started working on QUIC immediately. Like in 2014, 2015, people started to talk about like, we left some things behind in Speedy. We need to innovate. And a couple of working groups started inside the IETF. One was the QUIC working group, and then the other one was TAPS, Transport Services. And their idea was that we have like now a problem. We have ossification. We can't actually innovate on like new protocols. We can't build a new protocol. So the only protocol now we have is UDP. And if we can innovate on UDP, and we talk a lot about UDP and networking one-on-one as connectionless. So basically, you kind of move some of the responsibility that you need, that you got from TCP outside of TCP into UDP, and you say like, I'll build a layer on top of UDP that will do that same work, and that would be quick.
Just in the interest of kind of making sure that the audience is caught up, can you kind of quickly give us a high-level overview of the TCP versus UDP? What are the differences, and a little bit of history about where was UDP around when TCP was there, or
it was earlier? Like I think it was like a few years earlier was UDP. So UDP is what we call a connectionless, and TCP is called connection oriented. I think if you're a beginner, it makes a lot of sense. But as you grow into the world, like that separation only means that UDP comes with very few services. So if you're building on top of UDP something, you take responsibility to build all the services on top of it, right? And so TCP, what it gives is like, it's a connection oriented. So what does it mean? Like it's got a handshake. So it like talks to the other side, says like, it sets up the connection and says, hey, we have a connection now established. Now you can send data over this connection, right? Like, so you have a 4-way handshake or a 3-way handshake. TCP is in SYNAC, like people talk about that. So you do that handshake and then you say, now we have a connection we can set up, like we can. Now, if you can do that on UDP as well. Like you could create your own handshake.
But you'd have to build it yourself. It's not part of the protocol.
So basically, UDP is bare bones.
Even more bare bones than TCP.
Right. And it's actually quite difficult to get something built on UDP and pass, like, get an RFC, because there are so many people who look at it. And because you're not using any of the services that are already available on other protocols, then you have to resolve the problems that are like solved problems. So a lot of people did not want to build on top of UDP for obvious reasons, because like they would always get into this problem of solving solved problems, right? So when we came to do QUIC, it became very obvious that the solved problems that we had, like that TCP offered, were actually now constraints.
Becoming kind of like handcuffs. That they were constraints.
They were constraints, and you could not innovate beyond. Like, so basically, you had to resolve the solved problems, knowing what like the edge cases were, right? And now the edge cases were big enough that you would say like, we have to go solve this.
So when we get into HTTP3 and QUIC, what was the thinking around how to actually tackle this ossification issue? Has there been identified, or is there a strategy within QUIC that will prevent this particular thing from happening with UDP? And
actually, that's also a very good question. So QUIC has a versioning, and you don't like, basically, if you think of version numbers, most of them have like 2 bits. Like if you go down to the protocols and you say like, how many bits do I have? Like you have like 2-4 bits. You have a lot more bits on QUIC to like, so basically there's a version of QUIC that everyone agrees, and that's, let's say, version 1. That version of QUIC is what everyone's using today. But you could come up with a new version of QUIC, and like firstly you would probably need something like a browser or like an Electron app or like whatever. Like today you have native apps, so you could actually have like your own version of QUIC, which would be slightly different.
It would be for your native app.
And if you own the server side, like if you own both sides, you could have your own, and you don't have to like talk to anyone, right?
But you still have the middleman problem, don't you? You still have, wouldn't the middle boxes basically also prevent you, or they'll say, okay, we are...
Really good question, because like one thing that we skipped over that we talked about earlier, like why it took us like another 10 years from like Speedy to H3, and why we had to do H2, was we had to convince everyone in the world that we had to allow traffic over UDP. Because like if you think of a lot of networks, like even some ISPs drop like UDP, you can't actually send UDP across the internet. Partly it was WebRTC, which we'll talk about in passing. WebRTC emerged as a web real-time communication. It already required UDP. And it fought, for many years to like get UDP across a lot of networks. And even today,
Okay.
UDP gets blocked. Like if you're a hospital, if you're a bank, you're like some kind of enterprise environment, it's quite possible like UDP gets blocked. And then what you do is you go over port 443. So you masquerade UDP as a TCP transport, and like you basically find the nearest hop that you can go to over TCP. So there are edge servers. You connect over TCP, put your UDP packets over TCP, funnel it through that boundary, and then the other side it goes over UDP.
And then on the other side, go back to
Yeah.
UDP. Right. And QUIC is kind of built on this UDP
Right.
idea, right? So fundamentally, the middle box is basically the ones that WebRTC opened up for us for H3, basically allow UDP, and they don't actually realize that this is not WebRTC. This is actually
Yeah, and it's all encrypted, so it doesn't like basically it sees a UDP connection, and now if your YouTube stops because it's on H3, it can fall back to H2. But I think with time we'll realize that the performance of H3 is so much better. Like Netflix and all these people will require, like people who have relationships with ISPs where they find this UDP is blocked, will push really hard to get it unblocked, right? Because they would say like, hey, if let's say some geography in the world is having poor performance of YouTube or Netflix, people will like basically want better services. And we spend so much time today
absolutely.
on more than video calls, we spend more time on HTTP related services. And if they're actually degraded because they're on H2 instead of H3, like let's say VR, AR, like, there are bigger things that are coming that will push the boundaries. So I think the door's open. It just took us maybe like 5 additional years because of this.
Right. So yeah, the doors opened. And I think you mentioned also one thing, that QUIC was encrypted. So when you think about HTTP, we have this actually in-between layer. So you have IP, and then you have the TLS protocol in between, the TLS layer for doing the securing, and then you have HTTP on top. Is it the same thing with QUIC, or is this UDP, TLS, and QUIC, or is this something that QUIC does better?
No, I think
how does that work?
TLS is part of QUIC, like basically TLS, DTLS, TLS, datagram TLS.
Uh-huh.
So the main thing is that HTTP 1.1 did not mandate HTTP TLS. And I think until 2010, it was not even very common to see HTTPS on the internet. Like unless you were on a credit card site or something, you would see like this lock icon appear, and everyone was told to look for the lock icon. And then there was a big movement towards like TLS everywhere or HTTPS everywhere. And I think it is only this year or last year they claimed that 100% of the web is now on 99.9, like never 100%, because there will always be one side where it doesn't do something. But we're at like 4 or 5 nines now that everyone has HTTP certificates. And actually it's a very good question, because in 2010, if you said like, how would I get an HTTP certificate, it was very expensive. It was like $600.
Right.
And like most people who wanted to run a website, even if I cared a lot about security, if I was not doing credit cards, there was no way that I would like spend $600 for a certificate. So let's encrypt.
And that was a limited certificate as well. It was not even a wildcard certificate.
Yeah, you got like a very specific, And if you got a wildcard, it was like even more expensive, like 5,000 or 10,000 or something. Because
it was crazy. Yes. So okay, cool. So we have encryption in QUIC as part of the TLS thing. And I would imagine that kind of helps also, because it prevents the middle boxes from actually seeing whether this is a QUIC.
It's a losing game. Right? Like the Ciscos and the Junipers and everyone, I think they fought really hard to like protect their business. But it's also like, if you think about it, it took us 10 years to like kind of navigate around them and now have, UDP, and it took them 10 years. And if you think about what is the sunset period of someone who bought infrastructure is like 5 to 10 years, right? So basically they dragged their feet enough to kind of make sure that they were not caught off guard, and they built stuff in parallel to make sure that, and now they're building with AI ML, like all the security features that you think about, they've been like looking at the internet and said, if everything's encrypted, we will start to do like ML based encryption detection. So they'll never decrypt, but they'll just say like, oh, this type of traffic is X. It behaves like something.
Traffic shaping and traffic.
They'll look at traffic analysis and look at like destinations. And actually, this is why it's very important for us to move to V6, IPv6 as well. Because V4, like, there are only so many IP addresses. And if you know like the IP address belongs to Amazon, in some cases, you actually know what could be running on top of it. So if you get V6, then you actually make this problem much more harder because V6 has like almost infinite addresses, billions of addresses. And we also we are 7 billion people. So, we need probably like 1,000 devices each. And we're coming with IoT, everyone has so many devices at home.
Yeah, I imagine. IPv6 is definitely, I think, one of those things also that took a long time to kind of get in, and even now is kind of still slowly rolling out, right? But it is still part of the IP protocol, correct? So if you're moving to UDP and you're going to, assuming that every HTTP3 takes off, does that really matter anymore? Is that IP still... Well, I guess IP is basically the addressing, so it doesn't really matter. You need the addressing.
Yeah, you need the addressing. You need some kind of addressing.
Exactly. Now, we talked a lot about the middle box problem, the ossification problem, and the versioning in QUIC and the encryption, which kind of helps solve that ossification a little bit. But what else does QUIC actually have? What else does HTTP3 bring to the table, which makes it more compelling than HTTP2?
I think we should disambiguate the fact that HTTP is not like HTTP3 runs on QUIC, but QUIC is a lot more than HTTP3. It's not just the thing that would be on top of QUIC. QUIC has, you could easily build an application on top of QUIC, which is not HTTP, right? You would get a lot of like the same benefits. So you could think about, can we run WebRTC on QUIC, for example? Could we run, we talk about video streaming, right? And there are things like LS and Dash and like HTTP based streaming. Can we we need HTTP now that we have QUIC? Can we put media over QUIC?
Directly do streaming on QUIC
itself? Yeah, and we had this 25 years ago, right? Like if anyone's used Real Media Player.
Exactly. That was a proprietary
right, and it had RTSP, and you had RTSP ran over UDP, and you had real-time streaming protocol that was available. Yeah. But because of Adobe and Flash, actually people started to use Flash video, and then basically when Web 2.0 came and Apple, I think it was mainly Apple said we will not do Adobe.
Yeah, it is very famous. Steve Jobs said that we won't support Flash.
And then basically and then all those things Adobe that Flash did. right.
Yeah, it vanished overnight. So,
but I can talk a little bit about the features if you're interested. And
yeah, exactly.
So QUIC offers, when we had HTTP2, there were a lot of features that were part of HTTP2, which we moved into QUIC, right? So basically now H3 becomes simpler. If you go back to that semantics and syntax, semantics and syntax becomes easier because you move a bunch of things down. So for example, the TLS part, which was really important and you needed it for H2, was not mandated, but people wanted it moved below QUIC. So you don't have to worry about encryption and such. It's already guaranteed below. If you want to do end-to-end encryption in some form, you can do it anyway on top, but it's not really needed. It's the transport is encrypted. The other thing was zero RTT connection. So basically, if you look at session establishment, we talked about earlier that there was a three-way handshake or a four-way handshake.
Yeah.
And already in H2, we had a zero RTT, but really in QUIC, we got it for sure. Basically, if I've talked to you before, can we share some keying material from, can I tell you that, hi, we talked before and start sending you data, right? That's zero RTT. So the first time you meet an unknown thing, you would have to do all the four-way handshakes and everything. That's not. But the second time you meet, can you do it faster? Do you have to do the four-way handshake each time?
So assuming you have a cryptographic key from your previous conversation, you can continue the conversation.
Yeah, or you have some kind of keying material which would say hi, and I can challenge you and say are you the same person? And then because there was something that was shared before, you could say you could answer that challenge because you had something before.
Correct. Right. Okay.
So that was one. The other thing that we got was the congestion control. We talked about this, the initial window, and we talked about this AIMD, which was the very simple algorithm. No one uses that. People use things like QUIC and better algorithms. There's a new one that came out from Google called BBR, bottleneck bandwidth reduction. So BBR basically allowed faster shaping of traffic. So you basically got that in QUIC. You got customized congestion control. So if you don't like this, you can build your own. Again, you don't have to wait for a new version of the kernel. Head of line blocking, we talked about. Another one was migration. So if you have if I'm on my phone and I walk into Wi-Fi and then move to 4G and back, I can do connection migration without renegotiating the session.
Oh, that's interesting.
Right, because it's the same zero RTT benefit.
Idea. You still have the same connection ID. And that's since that is abstracted out of the whole UDP stuff, it doesn't. Oh, okay. That's interesting. Because I think in TCP, we have the header over there, right? That with the address. And it's kind of tied to your IP address.
So yeah, and you can just basically say hi again, right? And you just you're like, oh, you were that. And then you're like, okay, you're just coming from
So is that kind of wouldn't that kind of constitute from, I guess, a certain perspective, people being able to track you as you move across different networks?
I mean, that
right?
server would anyway be able to track you nonetheless, right?
That is true. Yeah. Cool. Yeah. Even when you eventually reconnect, you'd probably be sharing some cookie or session or something, right?
And actually, you moved it lower. Cool. So it becomes harder because you get this for free. In some sense, a lot of that tracking that you were doing inside the application, there is no need for it, right? So if you were doing any kind of tracking for reestablishment or connection, anything in service of providing better service, not just for ads and such, because in the case of ads, you definitely need it. But if you push that down, as an application, now you don't care about it. So you're not actually tracking at all, right? The thing that is tracking is not actually.
Yeah, you can still provide a good service even without having to put that ID into your application. It's part of the protocol.
And because of the head of line blocking, what that means is that you have partial reliability, and you can have something like partial reliability, right? So you can just say disconnect, I don't want that resource. So you can just say stop on many resets on any of these resources. And earlier resets was only on a connection. So you basically, if you said reset, you're saying goodbye, but you're not saying I don't want this anymore, right? So basically you could just say I can move on to the next resource. I can skip.
Oh, okay. So basically if you're okay, let's put it in video terms. Suppose I'm streaming a video and I want to pause this video or stop this video and then move on to another one. It doesn't mean dropping the connection, and you can just stop that video stream.
Yeah. So within a stream, it's in order. But because you have multiple streams, you can actually basically say, stop this stream, get the other stream. You can reprioritize. Yeah. So you get a bunch of these things. And you're right. So that's why QUIC is so interesting for a lot of us, because of course, if you're building YouTubes and such, and you're already on HTTP too, you want to use the same kind of semantics and syntax. But now you basically change the underpinnings without changing the application, right? So for that reason, H3 is really compelling. But it's also compelling for other things like web transport, for example, which is its own new protocol, which basically says that I want to use QUIC, but I don't want to use the HTTP semantics. I want to just, server initiated web transport. I want to just send data, stream you data. And if you're streaming data, not necessarily video, then you need something like a push in the old world. But if you have this, and you can just open a connection like a WebSocket and just say boom, I'm going to just send you stream data, and I'll open streams and close streams. Then you can just use web transport for it.
Yeah. Cool. That sounds really compelling. So how do you actually see this shift happening? I mean, you probably are in a unique position with your company and your background to kind of see. So how much in your rough estimate would be in the real world today? How much of my daily life is probably being run over H3 and I don't even know
YouTube,
it?
Probably.
And
YouTube, Facebook,
and a good bit of it, I imagine.
Facebook, YouTube. I'm not on Facebook, so I can't say anymore. But there are lots of the big services.
Most of the Google properties probably already do H3, correct?
But the ones that save the money, if you just think of it from a commercial or a capitalist perspective, it's going to be YouTube, for example.
So on the video side, is it not that compelling? Would I expect Netflix or... Yeah, that would also
not
be...
Not yet, but they have plans, I think. Almost every video provider has plans. But they're also thinking of media over QUIC, because it kind of opens a little bit more opportunity. If you think about HTTP as the ossification on HTTP, and now you have a QUIC, do you really want to be still on top of...
On HTTP, or just create your own streaming
on
kind
top
of
of
thing?
QUIC, and can we, you can certainly use QUIC version 1, what everyone's using, or you could have your own QUIC.
Yeah.
In the case of Netflix, it makes sense. You have a Netflix app, more or less all of us use some kind of app, either on an Android device, which is like a Fire TV or a Chromecast or whatever, or the television itself, which is an Android box.
Yeah, you can't get around the Netflix app because of DRM, right? It's an encrypted stream anyway. And so, like you said, yeah, they have the client and the server on these things.
I mean, you can do it on the web with the EME extension, like the encrypted media extensions. Like they can load the DRM and make sure that you don't steal it. But yeah, that is true. Like they own both ends, so it's fairly easy for them to start innovating. And I think there's a new activity called Media over QUIC that started only recently, like in last year. In one part of that problem is like if you think of RTMP, and I don't know how much our listeners know about it, but it's like basically a real-time media protocol for, if you have a webcam, if you have like a drone, they all have these RTMP endpoints, which, you can stream into that console or wherever. If you have a security camera, like all of them do RTMP, and all the live, right? Like, so a lot of these YouTube live and such, Twitch, like a lot of them allow for RTMP endpoints. So like if you don't want to like use YouTube directly to create your media, you want like you use OBS or something like that, then you can RTMP into YouTube live or into Twitch. And like, for example, at Daily, we offer, you're on a WebRTC call, and if you want just people to listen to you in that WebRTC call, like let's say all hands, you have like 10 people and you want like 100 people to, or thousands of people to watch the thing. You don't want them all on the call. You can move them to RTMP. Now, RTMP, for example, is an ingest protocol, as they say it. So if you're BBC or like, NFL playing a game and you want to broadcast that, the stadiums will have these RTMP cameras and that will stream
and then
into,
you just subscribe to them.
We'll go to Sports Center, and then from Sports Center, they would go out. So the idea right now is, can we solve the ingest problem with QUIC? And then you get basically new services on top of QUIC, Media over QUIC with this. And then you have WebRTC on the other side. So basically you could scale out to like hundreds of people or millions of people with WebRTC.
Actually, since we've been talking about WebRTC, I think it's a useful way to kind of round out this would be to talk about WebRTC and its rise and thing. Because I remember coming across WebRTC in the late 2000s. It was like 2010, 2011, 2012. I read this article and I was like, wow, this is kind of a really cool thing, because at that time, doing video calls and video chats and stuff like that was not common, right? It was a tough thing to do, and you had a lot of hacky ways to get streams together, and it was unreliable, and things used to crash and browsers used to crash and stuff like that. And WebRTC came at that time. I was like thinking about this, and it actually initially came out as a peer-to-peer protocol, and I think it still is an underlying. You can technically do a peer-to-peer connection between my browser and somebody else's browser directly.
Right now, it's likely going through peer-to-peer, like this call we are on is.
Yeah. So at that time, that was a very novel concept, because and so I was very interested. Can you give, given that your extensive background in WebRTC, I was just wondering, maybe you can give us a quick overview of how it started and, where it's reached, and where do you see this fit into the whole internet story?
You're correct that video calls have been around since the late 80s, early 90s. There was a program called QUIC. The main thing to think about, like the first 20 years of video calls was all about specialized people, specialized hardware, people who solved the problem, and there were specialized companies. Peer-to-peer aspect was actually, WebRTC was not that novel because you had Skype and some other technologies which were similar, which were already peer-to-peer.
Yeah.
And this kind of comes down to like, how the networks evolve. So Napster came out in like 2000, 1999, 2000, 2001, that period.
Right.
And that was like peer-to-peer music sharing, right? So
but that was also kind of a proprietary protocol. It was not over HTTP. I think what WebRTC brought it was over HTTP.
So basically there was this peer-to-peer stuff that was happening on one side. There was all the video stuff that was happening on one side. And Web 2.0, when it started, and Google basically brought Chrome and said like, now I have Chrome, and we have the Chrome browser, which will become the Chrome OS. That already seeded that idea. And then they said like, what are the services that are missing on the Chrome browser that are available on an operating system, right? And basically device access was one, and the other one was real-time communications, right? Those two things, right? So you did not have access to like a Bluetooth device or anything, like you didn't have mouse pointers. So they spun up inside the W3C, they spun up a device group. which basically said, I will find ways to like get access to peripheral devices that you would need access to from the browser, because the browser was actually never allowed to have access to anything which was local,
True.
right?
It was a
Right, it was
sandbox.
sandbox, and it could never access. It could only write, right? Like it could only write a file. Basically, it's like you download a file, it could just like download it, but nothing else. It could not read anything from it. So, like if you think about camera and mic, that's a change in behavior. You're now reading something, right? And you could always render. You had the video and the audio tags available, so you could always render, but you could not read. So that was one change. And the other thing was that as soon as you could read something, then you would say like, why can't I send my video across the internet? And WebRTC was basically not a new, like people talk about it as a new protocol. My opinion is that it was a snapshot in time of the existing protocols that existed at that point, so existing. And they basically said, here's a set of profiles across the whole stack that we are mandating. So what codecs, right? Like codecs, H.264 VP8. Okay. Next thing, RTP. What flavors of RTP? What flavors of encryption over RTP? RTP being the real-time protocol that carries the audio video, right? So like basically we think of that as a pipeline. You're like, oh, we now have standard interfaces in terms of API to access the device. We have standard protocol to send the media across the internet. And we talked about NATs and firewalls and middle boxes. So, if you're really peer-to-peer, you have to be able to open the ports. And there were already protocols for that. So like it basically said, we will use this flavor of X, this flavor of Y, this flavor of Z, and this became the WebRTC. And was really pushed by Google. But then when Google basically put the word out, then everyone was excited, right? Like Ericsson was excited, Microsoft was excited, because they're like, yeah, we'll do this. And we went out and did that. And I think the first spec came out in like 2012, 13, like the first draft, as we call them. And personally, I thought, we would have a big boom, just like with the web. So very clearly, like 1993, the web started, let's say, and by 2000 was big. 2012, 13, WebRTC started. And like the idea was that, in my opinion, I'm still bullish, and I think it was proven eventually that WebRTC would become the dominant protocol for video. And it did. Like it, of course, took a pandemic for all of us to like do like 100% of our traffic became like WebRTC at one point, because everyone was on calls for 8 hours, right? So it grew dramatically during the pandemic, but it was already really big before 2020.
Right. So how do you see this going the road ahead, right? So do you see WebRTC now going into QUIC and getting in more and more integrated into that side of things?
Yeah, so it's a suite, right? So WebRTC is a suite. So like as long as we don't change the API and like we just open another like just set a property in WebRTC which says like use QUIC, then we can just go down the pipeline and change a bunch of things. And to the developer, it would not matter if it's QUIC or if it's pure RTP over UDP. I think the main change that we are seeing now is what we would call unbundling of the API, because the WebRTC API is very, very opinionated. Like it was built for like a certain set of use cases, as you said, like it was peer-to-peer. But then we realized that for larger set of calls, the other peer can be the server, and then the server can basically, so it's back-to-back WebRTC connections in some form. And then you can create like, whatever topology you want. You can make a star, you can make a handlebar, like 2 big servers and like multiple fan outs on that side, or like some kind of mesh. So like for daily, we have a global mesh network, which connects everything, and you will connect to the nearest server. I'll connect to my nearest server. And, if there are hundreds of people, they'll all connect, and then we'll just transfer media across. So QUIC can play an important role here for sure. I think the biggest thing about the unbundling is, because of machine learning now, we need to unbundle in the middle. Like, for example, if I want to do voice recognition, or remove the voice, or like, background noise removal, or blur my background, unless the camera provides these services, I have to run some kind of custom machine learning right at the ends to be able to like do that. So there are things like there's like now a web codecs group. So basically you would have like the device captures codecs which are not from the camera or from the operating system or inside the browser. You can load your own codec. So, Varun's codec, for example, and then you encode it and then decode it on the other side with the Varun's decoder, right?
Right. And the codec will basically be built with the blurring, for example, inside
Right.
it. So you don't have to depend on a device or an endpoint. As long as you're using that codec, you know that it's going to be blurred. That's pretty cool. Cool. So we spent about a good hour on this and just wanted to kind of look back and ask you, is there something that you feel that we have not covered that we should cover? Or do you think that this is a good overview of,
I think we covered quite
like you said, 30 years?
Yeah, we covered quite a lot. Like we covered like 3 protocol families, HTTP, UDP,
Yeah.
TCP, and WebRTC, and on top of that. So
Yeah.
we covered a lot of ground. I hope the listeners find some value out of like this whole conversation.
No, I'm sure they would. I at least found a lot. So you have one person who has learned a lot. So thank you for that, Varun. And yeah, is there anything that you would want to talk about your company or?
I can give you like a couple of lines about Daily. So Daily is a video API provider. So if you want to build like a compelling user experience on top of video, this may be something which is just like peer-to-peer or like one person or few people talking to thousands of people. You can build that with a few lines of code. And we give you all levels of abstraction. So, no code, low code, mid code, full code, and the infrastructure that goes with it. So yeah, we want the API to be the most flexible API for most use cases. So we want to like cover, if there's a video use case that you have in mind and our API cannot solve it, we would love to talk to you to like get it inside the fold.
Cool. Is there any way, obviously I will be putting your LinkedIn profile and Twitter on the show notes. Is there any other way that you would like our listeners to
I think Twitter
contact you?
Place, or LinkedIn is also a good place these days.
Right. Okay.
Emails. I can give you my email and then you can share that.
Yeah, sure. I'll make sure that it's in the show notes. Well, in that case, all it remains is me to thank you, Varun. It has been a great hour. I didn't actually even notice that an hour had passed.
Thank you. Appreciate it.
So thank you for the time and the insights, and have a great day.
Yeah, you too.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.